So you're going to see that the heuristic iterative approach we proposed for the two-component normal is essentially the EM algorithm. Remember, we first compute the conditional probability of Zi equal to 1 or 2 given the data x and some initial value theta. And then we're going to update mu's and sigmas and pi using this formula. And in the EM algorithm, remember, we wanted to work with the joint likelihood of both x and z. So once we take log of this joint likelihood, we get summation. And zi's only appear in those indicators. So once we average zi, we have to evaluate what is the expectation of an indicator function of zi equal to 1. Well, this is basically the probability of zi is equal to 1. Well, since our expectation is taking respect to zi and given the data xi and some initial value of theta. So you're going to find out once we take expectation respect to zi, this becomes gamma I and this becomes 1 minus gamma I. And then you can work out the optimization over mu's and sigmas and pi, and they take this form. So where the algorithm is essentially the EM algorithm. But for EM algorithm, we still need to prove that it indeed, after iteration, it indeed improves the marginal likelihood of x. Meaning our algorithm can guarantee that after each iteration, the new value theta 1, the value at g of theta 1 is bigger than the value of g at theta 0 after each iteration. We wanted to show that this actually implies the marginal likelihood of x given theta 1 is actually bigger than the marginal likelihood of x given theta 0. That means each iteration of the EM algorithm indeed increase the marginal likelihood. Now, how to prove this? Let's first recall the definition of this g theta. It is the expectation of the log of the joint likelihood of x and z, and here the expectation is taking respect to z, conditioning on the data x and theta 0. So no matter what the value of theta, and the expectation is always taken with respect to z given x and theta 0. So what is the difference of g theta 1 minus g theta 0? The expectation is the same, so we keep the same expectation. And the difference of the log becomes log of the ratio, and theta 1 is on the numerator, and theta 0 is in the denominator. And then we're going to factorize this joint of x and z as marginal of x and conditional of z given x. And we will always carry theta around because theta is basically the parameter for those distributions. And then we're going to break this big term inside log as a product of the term on the left of this bar and the term on the right of the bar. But the ratio on the left of the blue bar doesn't depend on z, so we can take it outside the expectation, which is this term. Now, for the term on the right of the blue bar, we keep it and we flip the numerator and denominator. So now theta 0 is on the numerator. And then we're going to add a minus sign in front of this. Okay. So we have this equality and we rearrange it. We have this term is equal to this difference plus this term. So this is what we have here. Now notice this term is the KL divergence between two distributions over z. And so it's always non-negative, bigger or equal to 0. And our algorithm, the way we do our M step, guarantees that this difference is positive, bigger or equal to 0. So we can show that the left-hand side is also bigger or equal to 0. That means this ratio is bigger than 1. So we have this conclusion.